Giorgio announced the title, so let me just point out the list of collaborators I have in this project. And I hope that you listen to the talk of Jack McLeod, which was a great one, as always. And this talk will link to Jeff's talk in a way that Jeff talked about what happens when we do continuum modeling of X-ray binaries in the range of luminosities which are from or around 0.1 Eddington, from 0.1 to 0.3. And my talk will tell you something about what happens when we go to higher luminosities, that means from 0.3 higher. This is an illustrative plot of the results which the continuum method gives for GRS 1915, taken from Jeff's paper. And the important thing to see here is that below 0.3 Eddington, the results which we get are pretty consistent. Every observation which is analyzed gives the same value of the infrared spin. However, when we go beyond this threshold value in luminosity, it's no longer the case. The value of spin which we infer from the spectra continuously are smaller and smaller. It shouldn't be the case because we know that spin of the black hole is a constant thing. It cannot change on a time scale of days. So what this tells us is that the model which has been used here, and it's a Novikov-Thorne model of accretion disk, works pretty well in this regime of luminosities, but does not work that well for higher luminosities. And that brings us to a question of what's wrong with the model, or how we can improve on this. And it's not only the case of GRS 1915, so one source. It's also the case of, for instance, LMCX3. Here is the similar example, although the quantity which is plotted here is not spin, but it's the inner measured inner radius of the accretion disk. So that's why you don't see the drop here, but rather increase. But it's the same thing. It's just the whether you plot the disk radius or the spin. Again, the message here is that for the range of low luminosities, the spin which we measure is pretty constant, and here something happens with the disk, and it's not longer the inner radius which we measure is no longer constant. And the same thing, this is from our paper, or the Stroud paper. Here you can see the spin versus luminosity as it goes down. This plot compares two different models. One is KERBB, which is based on Novikov-Thorne radial structure of the disk, and the other model is SlimBB, which is based on more advanced, or at least we thought would be more advanced model of the disk, which is called SlimBB, and it relaxes some of the conditions which are in the Novikov-Thorne. Namely, it allows for advection. This is most important effect. But you see from those plots that the results which we get are more or less the same. We do a little bit better. For instance, here you see a red line, which is the average, is slightly above what is the average of the KERBB fits. However, the same thing here, whenever we go beyond 0.3, the spin goes down. So, and we started this project with SlimBB because of this. This was the motivation, such a plot, because we thought that the advection, which is missing in Novikov-Thorne, and therefore in the KERBB model, would be the key ingredients to fix such a behavior. But it turns out that it's not the case, that the advection doesn't help very much. On this plot, it's shown that indeed this is a genuine effect. It affects all the sources which have ever been analyzed by this method, and they do all show the same thing. Namely that you can measure constant radius until a certain luminosity, and once the luminosity is higher, then what you measure is no longer constant, but there is apparent increase in the radius of the disk. I say apparent increase because it doesn't necessarily mean that there is indeed an increase in the radius of the disk. So the disk pushes out. But it can easily mean that the disk, there's nothing wrong with the inner edge of the disk. It may be still well at the ISCO, but simply our model of the whole disk, the whole structure of the disk, is not all right. So then we are left with these two options. So either we really think that the inner edge of the disk expands and it doesn't stay at ISCO for higher luminosities. That's one option. The other option is that the nature-produced spectra for higher luminosities are much softer than what is predicted by our models. And if the actual spectrum is softer, then when you model this, when you try to fit with a model that is harder, it would make this effect which you observe, that your spin which you measure will be lower than the actual value. So between the two options, I personally am not comfortable with this one. So in the rest of the talk, I will expand more on the second one. So the crucial question is then what to do or what to assume to improve our models, and how to make the spectra which we predict softer. I should say a few words about how these models are done. So first of all, one has to have a radial disk structure, which means a radial profile of temperature, surface density, angular momentum, and also other quantities. But these three are the most important. They tell you what is the temperature in the disk, which means what the radiation comes out, and the surface density tells you something about the opacity, and the angular momentum about the velocity which the disk moves around. Then, having this, you can do the radiative transfer in the vertical profile, which means you do the decomposition. You first define your radial structure, and then you take this radial structure and you divide it to the set of rings. And then each ring you treat separately as a plane parallel layer of atmosphere, and you do the radiative transfer in this infinitely wide plane parallel layer. And then after that, you integrate over the surface, do the ray tracing, and then you have to find a spectrum which you put into the expect model, and then you fit against the data. Okay, here are a few examples about how the temperature goes within the profile. Just it's not quite important. Here is the spectrum, and you see the dashed line corresponds to the black body as it would which tells you how the spectrum would like for an effective temperature, and this solid line is the result of this radiative transfer calculation, which gives you slightly different profile. As it concerns the radial structure, as I said, the mostly used radial structure profile is given by the Novikov-Thorne thin disk model, which we know is quite solid at this luminosity, close to 0.1, plus minus 0.1, let's say. It has been confirmed many times by fitting the data. The Harvard group also did a comparison with GRMHD simulations. And it seems to be quite solid. However, it's not supposed to work at high luminosities because there are assumptions which are not met in this regime. So we came up with slim disk, which was supposed to relax some of those assumptions. I said it allows for advection. It also allows for non-Keplerian angular momentum profile. And these effects come in, and that they really can be seen in the spectrum, which then comes out from this model. But the change is noticeable only when the luminosity is greater than 0.5 Eddington. And then from the data, however, we see that the problems start already at much lower luminosities, between 0.2 and 0.3. So this slim disk does not really help us very much. And there is something else which happens to the disk, even at lower luminosities, that this slim disk effects, advection, and so on take place. For the vertical structure, the high luminosity disk usually predict, or our models of high luminosity disk usually predict very high hardening factors. Hardening factor is a ratio between the effective temperature and the color temperature. So the effective temperature corresponds to the amount of flux coming out of the disk, and the color temperature describes the spectrum which comes out, and that can be distorted by effects in the atmosphere and so on. These hardening factors are usually around 1.5, 1.6, but here, when we model the high disk profile, we found that the hardening factor in the spectrum can be greater than 2, which is a lot. And that is also a genuine effect in several codes. There are at least 3 numerical codes which can calculate the radiative transfer within the disk profile. And they all agree more or less about that there are as high color factors as 2 in such luminosity disks. So it means that the optical depth gets too low, and that violates some of the assumptions which are in the models, because the radial disk model assumes that there is a diffusive approximation that makes the spectrum, and if you have optically thin disk, that this diffusive approximation is not valid, at least in this upper part of the disk atmosphere. It is still valid in the mid layer, but the radiation is mostly depends on the structure of the upper part of the disk atmosphere. So already here there's a problem which tells you that something is not all right. And then also, obviously, for high luminosity disk, if you have advection, then this approximation, this thin infinite parallel layer, does not hold, because this assumes that there is no advection here. And the advection connects two different the rings which are next to each other, and must be also carefully treated. This plot shows how this hardening depends on alpha, because alpha is a free parameter of the model, at least the slim disk model. The logical model is independent of alpha. But in slim disk model, we can change the value of alpha, and this plot suggests how. So here are 5 different panels, each shows a different value of alpha, starting with alpha 10 to minus 1 and going lower and lower up to 10 to minus 2. And then this plots the value of the hardening factor as a function of luminosity. So you see for the highest alpha, so we also get the highest hardening factor. And then it goes down. For the lowest alpha, we have lowest hardening factor. That is connected to the fact that the lower value of alpha means larger surface density, and then reduces the hardening because of increases the optical depth. So we can use this to just play with the data. And we can use, this is an example of data of LMCX3 where we used the value of spin which we measured for from the lowest luminosity data, and then we take the rest of the data, which goes with luminosity up to 60% of Eddington, and then we fix, in the fitting, we fix the spin, and we fit for alpha, and mass accretion rate, of course, so the luminosity. And this is what comes out, obviously, because the previous profile was like that, the spin goes down. So now, if we change alpha, and we change alpha in this way, so that with increasing luminosity, the alpha goes down, so the hardening factor goes down, and then we are able to fix this yellow points. We fix a value of spin, but at the expense of the fact that alpha is changing. But that obviously is not the answer, because first of all, what is the reason for this, that alpha goes down, and also you cannot go with alpha to 0. So already here you see that we finish at let's say 0.4. This is when we reach our lowest value of alpha 10 to -2. But the data, it goes up to goes with luminosity even larger, to 60% of Eddington. And these are the part of the data which cannot fit this any model, assuming the lowest possible alpha. There's another effect which has to be taken into account, and that is self-irradiation. This is especially important for high luminosity disks, because contrary to the low luminosity disks, which more or less live in the equatorial plane, and the vertical extent is quite small. So for this high luminosity disk here, that's represented by this orange profile, you see that the path from photons which are emitted from this point, which is the one which radiates most, they actually, due to light bending in the strong gravitational field of the black hole, have quite easy way and then can irradiate the opposite part of the disk. So there's a significant amount of energy and also angular momentum, which is transported by photons emitted from this place to this place. And then it provides additional energy input, and also must be then dissipated in the disk. So this plot shows how big this effect is. Here it is for Novikov-Thorne, assuming that the disk is in the equatorial plane, and as a function of spin and luminosity, it shows in color how much of additional irradiation the disk gets, and indeed it should be it does not depend on luminosity, so the contours here should be perfectly vertical. But because of numerical precision, which is not the best, you see that it's not perfectly vertical here. However, let's say for the highest spin, the maximum value is a little bit more than 7%. It's 7 point something. Which, okay, you can either neglect, or you can account for this just by changing your mass accretion rate a little bit. For the slim disk, however, the situation is much different, and then you see, if you take account the proper vertical profile, the location of the photosphere, that this amount for the largest spin and the highest luminosity can be more than 25% here. So that's quite huge. Let's skip this, and well, maybe I'll show you, because still 5 minutes. So this plot just shows the balance of the flux. So we plot flux against the radius, and what you see, let's take this example of the high luminosity and high spin. So what you see in red here that's the Novikov-Thorne profile of flux for the highly spinning black hole with 1 Eddington luminosity. And then what you see not very well with green is the contribution of the returning radiation, and the blue curve makes the sum of those two. So if you compare the blue against the red, you see the contribution which is extra and which has to be accounted for. Okay, so now we know that most processes which we can possibly include in the spectral modeling of accretion disks, perhaps definitely except for abretion, which makes the spectrum softer, all the others make the spectrum which we model harder. But that's not what we want. So coming back to my original question, what we can do or assume to make it softer. And then the question number one, the answer number one, which is here, is that we should somehow account for these outflows. Because it is obvious from analysis of data or from MHD simulations that there is something which happens to the disk at this, more or less at this luminosity, which there is some outflow onset in the disk that alters the disk structure. Therefore, it modifies the emergent radiation, and this emergent radiation is further processed in the atmosphere of the disk and in this outflow, which goes parallel to this disk surface. In GRS 1915, we see this. You can read the papers by Joey Nielsen, where he shows that definitely we see a mix of the primary radiation with a quantonized component. In LMCX3, you see in the spectra which Chris Don showed this morning, they all look beautifully like a disk, but we know that it cannot be a pure disk. There has to be something else, because the model which we used cannot fit those spectra. And for other sources, it's the same story. So the effect of this outflow is the following. First of all, the disk structure is changed because there is a mass flux coming up to the surface from the disk. That changes the emission spectrum because the disk profile is no longer what is assumed in the model, KBB or SLBB. And then these photons are then processed in as they pass through this outflow. And of course, the wind take energy of the disk photons by the fact that either the photons are scattered out of sight or simply they are processed in and the shape of the spectrum is different than we assume. Here are two plots. One is taken from one of the Joey's paper, and the other one from the Oleksandrovsky paper, which argue, both papers argue on the same effect, this from the observational point of view and this one from the theoretical point of view, so I suggest to have a look. And to sum up, I just say that for the low luminosity accretion disks, we are pretty confident that the spins which are measured are the right, more or less the right values. It's on solid ground. While in the high luminosity regime, the spectra which we have in the data are much softer than what we model. So we need improvement in the radial structure modeling, and also connected with the vertical treatment of the vertical structure. So far it is done independently, so the radial structure is constructed first, and then on top of it you calculate the structure of the disk. But there should be an effort, and there is already such an effort to combine those things into a self-consistent treatment, both radial and vertical structure in one calculation. All right, the advantage of course, is that we already have the value of spin measured for the lowest luminosity. So we can take this as a reference value, and all the further modeling we can compare with this result. So we are not starting from zero, but we are starting already from something. Okay, that's it. Thank you.